Okay, this is the first video in a series on acid-base chemistry, and what I'm going to do is mostly focus on definitions in this particular presentation, and I'm going to focus on the acid-base definitions of what I think it will be the most common focus in any chemistry class, and that's going to be the definitions concerning Bronsted-Lowry acids and bases. All right, so let's go ahead and get started. The basic definition, or the standard definition of an acid by Bronsted-Lowry, will be any substance that donates a proton in a proton transfer reaction. Transfer reaction, and I'm going to abbreviate reaction as RXN. All right, now I'm going to mainly focus in this presentation on acids, but you can't talk about acids without also talking about bases, because they're completely interrelated and you can't have one in solution without the other. So we're going to go ahead and define the Bronsted-Lowry definition of a base too, and we'll definitely apply this. So a base is going to be any substance that can accept a proton in a proton transfer reaction. Okay, now if the viewer is new to chemistry, most often the question I get is, how do you tell an acid when you're looking at one? And that truly is an issue if you're a beginner. And so what I've done here on the right side of the screen is I've listed what are called the classic 6 strong acids. All right, so over here I've listed the 6 strong acids, and I'm going to define the word strong in a few minutes. For now, we're going to let it go. The main thing is that all 6 of these molecules are acids, and what you'll notice about all 6 of them is that each of them have a hydrogen that appears on the left side of the formula. All right, and then in the definitions I use the word proton, and the reason that I'm using that term will be more apparent in a second. So let's look at an example. So I'm going to pick on hydrochloric acid, that's HCl, because that's most often the strong acid that is focused on in textbooks. So let's take a look at what happens when you take hydrochloric acid and you dissolve it into water. And by the way, I should mention that oftentimes in the beginning of these descriptions in a textbook, they talk about the fact that when you dissolve an acid into water, that the resulting solution is going to have a sour taste. So the viewer might just take a moment to think about what orange juice tastes like, lemon juice, grapefruit juice, and things like that, because those all have sour tastes, and the reason that they do is because those solutions are in fact acidic. So if we take hydrochloric acid and we dissolve it into water, we produce 2 products, H3O plus and Cl minus. Now let's talk about the H3O plus here for a minute. This in fact, this molecule, and I'm going to rewrite it over here, I'll change the color. So H3O plus is in fact, as long as we're talking about dissolving an acid in water, this molecule is analogous or the same as talking about a proton. because what's happened when you take an acid and you dissolve it into water is that the hydrogen that I showed up here with a red asterisk next to it has actually been donated to the water molecule. So this hydrogen that I'm drawing an arrow to here is donated to water. And you can see that when you do that, now you've got a situation where the oxygen in the water molecule is bonded instead of to 2 hydrogens now to 3. So as long as we're talking about a situation where we dissolve the acid into water, all right, then H3O plus is the same thing as a proton or the hydrogen ion. So let me continue with the definition. So these things are all the same as long as we're dissolving an acid into water, so hydrogen ion. And formally, the H3O plus is called hydronium. Hydronium ion, all right? So this is important that you understand all these terms mean exactly the same thing as long as we're dealing with an acid that has been dissolved in water, all right? And more than likely, as I go through this presentation, I will in fact use these terms interchangeably. So you need to understand that they all essentially mean the same thing, as long as we're dealing with an acid that is being dissolved in water, all right? So the context is important here. Now, let's go back to this example, and I want to address the issue of the term strong. So hydrochloric acid, when you add it to water, is going to ionize. That's what we call this. You see what happens here is the HCl splits apart, and the hydrogen ion, again, I'll just keep emphasizing this, is dissociated or removed essentially from the molecule of HCl, where the H is transferred to the water, becoming H3O plus, and then the chloride becomes free base. Now, definitions. This is the acid. We just defined it that way. And in the context of the water, look at the definition of the base. All right, a base is any substance that can accept a proton in a proton transfer reaction. And you can see that what's going on here when we take the hydrochloric acid and we dissolve it in water, that the water molecule is actually accepting the proton. All right, it is accepting the proton. It accepts the proton. And therefore, in this relationship, the water is actually operating as a base. So I'm going to go ahead and label it that way. Now, when we look at the right side of the arrow and we evaluate the two things that were produced in the reaction, you can see that by definition the H3O plus is acidic because it has a proton that can be donated to something else. And so this thing is actually an acid, but we're going to call it, instead we're going to call this a conjugate acid. It's a conjugate acid, and we call it a conjugate acid because its origin comes from the H2O, all right? Because the H2O is the thing that actually accepted the proton from the hydrochloric acid. So we would write that the H2O is in a relationship with the H3O plus. So this is going to be a base, a base conjugate acid pair. All right, and then we've got our hydrochloric acid, which is in a relationship with the Cl minus, and that is what we call an acid conjugate base pair. Acid conjugate base pair. All right, so this guy here is, to finish the labeling, is the conjugate base. Now let's deal with the issue, this word strong. What does it mean exactly? All right, for the strong acids, let's say that we started out by, if we, and this is a simple argument, but let's say we started out with 1,000 molecules of hydrochloric acid, and we're able to count these molecules up, all right, in theory. I mean, you can't really do that, but in terms of how a normal person thinks about counting. But let's just say that we've got 1,000 molecules of hydrochloric acid, and we add those 1,000 molecules to the hydrochloric acid. And I think in this example I'm going to quickly move my equation down here so it's easier to see what I'm talking about. So I'm just going to rewrite this here where we have some extra space, and it's going to be H3O plus the Cl minus. So let's say at the beginning of the experiment we take and we collect 1,000 molecules of HCl, and we plan to add that to water to make a solution. So in the beginning, before we add it to the solution, there's going to be 0 of the H3O plus and there's going to be 0 of the Cl minus. Now we go ahead and we splash the hydrochloric acid into the water, because acids come as liquids. All right, so this is going to be a liquid. So we have 1,000 liquid molecules, we add it to the water and we mix it up. Now here's what happens. After the reaction is over, all 1,000 molecules of the HCl are going to be gone in this form. This form does not exist once the reaction has occurred. And instead, we're going to have 1,000 molecules of the H3O plus, and we're going to have 1,000 ions of the Cl minus. All right, so we're going to have 1,000 of the H3O plus and 1,000 of the Cl minus. So basically, strong acids, the word strong means that, so strong acids ionize to 100%. All right, now notice down here at the bottom of the screen I've included 2 additional acids. These guys are called weak acids. Weak acids, and I chose these because the viewer, they may not realize it, but they have experiences with both of these acids. Acetic acid is actually vinegar, and I'm certain that most people who view this have had vinegar and oil dressing salads. And then citric acid, which appears, which is in lemons, any of the citrus fruits like lemons, grapefruit juice. This is the acid that causes the sour taste in those particular fruits. Now, these are called weak acids, and these are weak acids because when you add them to water, they do not ionize to 100%. So let's say that we had, if I rewrite my acetic acid here, that's the simpler one to work with. Because it only has 1 proton that's going to be donated to solution. So I'm going to put an asterisk next to the H that's going to be donated in each of these cases. So in the citric acid, it's going to be this proton, and this one. Notice that citric acid actually has 3 protons that can be donated to solution. So we call this a polyprotic acid. Polyprotic because it's got 3 hydrogens it can donate. The vinegar or the acetic acid we call monoprotic because it only has 1 hydrogen that can be donated. Monoprotic. Hydrochloric acid is also monoprotic. If you look in the strong acids, you'll notice that H2SO4, sulfuric acid, is actually polyprotic. I'll come back to that strong acid in a different video. But to focus on the matter at hand, if we look at acetic acid, and when it's put into water, so there's a reaction with the water, all right, we're going to form H3O plus like we did with the hydrochloric acid. And in the case of the acetic acid, though, we're going to have a different we're going to have a different anion. It's going to be this one, which is actually got a name. It's called acetate. All right, now getting back to the matter at hand, these are called weak acids because if we did the same experiment that we did with the acetic acid and we put 1,000 molecules of the acetic acid into a beaker with water in it, after the reaction is over, there is only going to be, out of 1,000 molecules, there's going to be 996 molecules that are not ionized, and we're only going to have 4 molecules that actually ionize to produce the H3O+. So you see the difference between a strong acid and a weak acid has to do with the level of ionization. All right, and for strong acids, they ionize completely. So if I have 1,000 molecules of any of these strong acids, when you add them to water, they produce 1,000 molecules of the H3O+ or 1,000 H+. And with that, I think I'm going to go ahead and close this video.